Here. Okay, I hope you all had a good break. So our next speaker is Dr. Jihyun. He's a medical physicist at the Cross Cancer Institute and assistant professor at the U of A. His clinical work at the Cross involves the management of the linear accelerator, the gamma knife icon, and the linac-based SRS. His research involves real-time tumor tracking using the linac-MR, and he was responsible for the world's first demonstration of real-time tumor-tracked beam delivery using the linac-MR. He also incorporated machine learning and deep neural networks into tumor auto-segmentation algorithms in MR images and tumor motion prediction algorithms. In addition to this, Dr. Young teaches several university oncology courses that incorporate the principles of medical physics in patient care. Please welcome Dr. Young for his talk on AI for the most accurate radiotherapy of mobile tumors.
Thank you for the introduction. Can you hear me well in the back? Okay, good. So just time myself. I'm learning a lot today. I hope you are too. Just learned about finance words just before. I'm Jihyun. I'm a medical physicist at the Cross Cancer Institute. I'm also an assistant professor on the oncology at the University of Alberta. I'm a user of AI rather than a professional AI scientist. So in that sense, many of us are in the same boat, right? So what I'm hoping to do today is to provide you a couple of examples of using different types of AI for either an academic or clinical research project, just to share my experience, my thought process, and then of course my mistakes. There are tons of them, so you don't have to repeat them, hopefully, when you do your own research. So to that, I have to talk about a little bit about my research project, so you'll know why I am doing, why I'm picking this specific type of AI for my project. And then I'll focus on those couple of examples of AI and then finish with some experimental results at the end. So my project is to achieve the most accurate radiotherapy of mobile tumors in the Alberta linac-MR system. And of course, none of these should make any sense to you right now. But by the end of my talk, hopefully, at least the title will make some sense to you. Then I'm good. Just a little bit about radiotherapy. This is a big deal. We have more than 14 million cases of new cancer patients every year globally, and more than 50% of them will go through some form of radiotherapy. Radiotherapy uses ionizing radiation to kill cancer cells, which is a good thing, but then unfortunately, it kills the healthy tissues too, which is a bad thing. So this is the machine. Maybe I have a... Oops. Okay. So this is the machine that we use to generate ionizing radiation and treat patients. It's called linac, linear accelerator, right? And the goal of radiotherapy is to maximize tumor radiation while minimizing normal tissue radiation. Make the radiation beam as thin as possible, as accurate as possible, so we can only attack the tumor cells without killing the patient. Right? So what's the challenge? Medical physics, we're doing awesome job if, and this is a big if the tumor is not moving during irradiation. The perfect example is the brain tumor. So you see these 3 brain mets here. We can actually physically fix the skull using this type of frame or a mask. So in this case, nothing's moving during irradiation. We can deliver sub-millimeter accuracy radiation if this is the case, and it comes with minimal normal tissue toxicity. So we're doing great here. Problem starts when the things starts moving, like this lung tumor here, moving up and down, left, right, few centimeters actually, right? And the worst thing is most tumors are moving because of breathing or cardiac motions. So this comes with worse geometric accuracy because by the time we shoot at it, it moves. and it comes with larger normal tissue toxicity. So what do we do about this now? This is total exaggeration. This is not what we're doing. This is just for visual purpose in this talk. Imagine that red structure moving is a moving tumor, let's say, and then the black structure is a critical organ next to it, like a kidney. We irradiate large margin around the tumor to make sure we cover the entire motion path of the tumor. And of course, this is to kill all the tumor cells. We don't want them to recur at the end. But in doing so, we have to irradiate lots of normal tissues and the critical organs too, right? So rather than doing this, what I like to do is called NIFT-RT. We coined this term, stands for non-invasive intrafractional tumor tract radiotherapy. Intrafractional here means during irradiation, okay? So rather than doing conventional RT, can we just focus on the beam on the tumor only and then chase it in real time, right? And I can do this because I can use this device here, if you can see it, yeah. This device called multi-leaf collimator. You can think of it as a real-time radiation shaping device that I can control using software, okay? So in this case, of course, we can minimize normal tissue and critical structure radiation. Obviously, I'm not the only one with this idea. Medical physics community over the last 100-some years knew that this is way better. But the main reason we haven't been able to do this is because there's a prerequisite. I must be able to see the tumor clearly during irradiation, right? If I can't see the tumor, I can't treat the tumor. And another problem is most tumors are soft tissues, right? We have X-ray based imaging that can do really, really fast, like fluoroscopy, right? But that doesn't show me the tumor. That's the problem. And what's the best imaging modality to see soft tissues? It's MRI. So people have been thinking, can we just combine these two machines into one? Then we'll have best of the both worlds, right? Can we MRI during irradiation? And it was considered not possible for a long, long time because of many reasons like electromagnetic interference, RF noise, blah, blah, blah. These two machines are just allergic to each other. You can't put them together. But medical physics community didn't give up on research. So after 20-some years of research, now we have this machine, the hybrid linac plus MRI machine. This one that I'm showing here is called Alberta linac-MR. So you have linear accelerator at the top, and then you have MRI on a rotating gantry. So we can shoot the beam from different angles, right? This was invented by this gentleman here, Dr. Jihyun. He's also a director of medical physics at the U of Alberta. He's quite happy in this picture because this was the day that we treated the first patient in his machine at the Cross Cancer Institute, right? This is the actual treatment room. The machine itself is behind this cabinet. So this is gantry at 0. It rotates. So this is the gantry at 90. And this machine can provide MRI. As you see here, this is a volunteer image. So now I meet my prerequisite. Now I can see the soft tissue tumor during irradiation. So this machine is the only reason I can still continue my research project, which is to do clinical implementation of NIFT-RT for mobile tumors in Alberta linac-MR. I need to go through several steps to make it possible. So first step is, of course, the fast MRI. So I'll have images like this one here. This is a lung tumor image. Once I have this, next step is to figure out the shape and the position of the tumor in each of those images. And this step has to be automated. No human beings can contour manually the tumor in every quarter of a second, right? Once I figure that out, now I can start conforming the radiation beam using multi-leaf collimator. If I don't do anything here, then the beam actually will be always lagging behind the actual tumor motion because everything here takes time. Image acquisition, auto contouring, the mechanical movement of each of these leaves These are thick tungsten leaves driven by a motor in the back. So that takes time too. So I had to put some sort of motion prediction capability, right, to compensate for the tumor motion during the system delay or time delay, we call it. So once I input the current tumor position, which is the centroid of the contour, then the software will output a future tumor position considering the amount of time for the tumor motion, right? Then I can start conforming the beam, and hopefully by this time, the beam and the tumor will be in perfect sync, right? So every steps here, they have to be repeated for every single MR image, which will come in every quarter of a second. So I don't have that much time. It has to be really fast. And during that time, the radiation beam will be always on. So this is the overview of NIFT-RT, but today I'm only gonna talk about step number 2 and then step number 3, because those are the steps that I use the AI so far. So first example, tumor oral contouring. This is a critical step because if I don't get this thing right, everything else will be just plain wrong. So I developed many algorithms using edge detection, one type of AI called pulse-coupled neural networks, another type of AI called, we all know, deep learning neural networks. The reason is my problem is quite unique. I want my algorithm to exactly follow the manual contour of an expert. In our case, that's radiation oncologist. Even though everyone else says the tumor is totally circular shape, if a responsible radiation oncologist says, no, this is total triangular shape in my clinical opinion, then I want my algorithm to exactly follow that triangular tumor shape. That's a unique problem. Again, and then my software is meant to contour tumor, not the healthy tissue or organs at risk. There are tons of other softwares out there doing that job, but I want mine to contour the target, which is a tumor. And it has to be fast. I only have about 50 milliseconds of time budget to auto contour each image. And the aim here is to have more than 90% auto contouring accuracy for 3 tumor sites: lung, liver, prostate. Okay. So this is the one that I started using in terms of deep learnings. The original UNet structure is quite famous. I don't need to go over this, right? And the reason why I picked this structure is I really wanted to have an algorithm that does human-like contouring. When we contour, we have some abstract shape of tumor in our mind using our experience or education. And then when we actually contour, you go through the boundary between the tumor and the background, right? So I was looking for an algorithm that can mimic that process, and UNet seems to be a good balance. Going through this convolution and pooling layer, right? You're essentially extracting the abstract shape of the tumor, and you're denoising the initial, like original image, which is a good thing. And luckily, it has this up convolution structure where it reproduces the original resolution. So I don't have to do a lot of post-processing. At the same time, it has this concatenation layer where it's not exactly the original image, but close enough in my mind. So maybe it's a nice balance between using abstract shape as well as spatial information. So I took this, tried it, and it worked well for lung tumor cases, not very well for liver and prostate cases. And at the time, I had a PhD student interested. So we were discussing, how are we gonna make this thing better? And we thought, you know what, maybe we don't need this big neural network structure for our purpose, because our MRI image, those are resolutions relatively low. We're never gonna work with 4K or 8K images, right? Because the imaging has to be really fast. So why don't we make it slim? Then it will make it faster, which is exactly what we want. And another idea was that why don't we focus on to each patient? Because each patient's tumor shape, tumor motion, they're quite unique. So if we can come up with an algorithm that can optimize the network structure for each patient, that may work better, right? So we went through different types of algorithm to do hyperparameter optimization. Hyperparameters are the ones that decide the network structure, which is a critical portion of its performance. So we were optimizing parameters like number of convolution, number of downpath, number of training images, and then found that a very simple structure. So this is just one example because each patient has its own structure. So this is one example. Mostly we have just one pooling layer, that's good enough. And then 42 feature maps compared to the 64 in the original UNet structure. So much simpler. And because this was simpler, it took less training and execution time, which is exactly what we wanted. And it actually performed better for lung and prostate cases, about the same performance for lung cases. So these are a few examples. Lung, liver, prostate. Red contour was done by an expert, a radiation oncologist. Green contour was done by the software. And then I'm giving you the dice coefficient in between the two, showing the agreement. And these are all difficult cases. In lung case, sometimes we have this diffuse tumor boundary between lung tumor and the healthy tissue, and it's intermittent. Sometimes it's there, sometimes it's not. Maybe it's image artifact. So my previous algorithms based on edge detection was always struggling, should I take this part as a tumor or not? But the UNet-based algorithm was quite smart. It followed the manual contour. Okay, so this portion was never been contoured as tumor in manual contours. So it drew a line right there, excluding that portion. I was very happy to see this performance. Liver cases are even more challenging because there's a very little contrast between the liver tumor and the healthy liver tissue. If you look at this portion, where do you draw a line? There's a very gradual decrease in contrast, right? But again, the new algorithm was able to draw a line following the manual example, as you see here, especially in this hypo intensity area where it's about the same from here to there. So it's kind of hard to see, which part is tumor or not, unless you use this abstract information. Prostate is another interesting case. In radiotherapy, we treat the entire prostate. That's the target. But sometimes we include seminal vesicles. Sometimes we don't, depending on the physician's choice or patient progression. If we decided not to include seminal vesicles, it's more challenging because there's no boundary between the seminal vesicles and then the prostate itself, right? But again, UNet-based algorithm was quite smart. So we applied this algorithm to more than 30 patients of in vivo MRI data, and then achieved more than 90% accuracy for those tumor sites. And this is just to give you an idea how it should happen in real time. So I'm running these images every quarter of a second, and the tumor should be auto-contoured as you see here. So that's the speed that I have to deal with. Okay, so that was first example. This is a second example. So here I'm using AI for tumor motion prediction. And again, this is to compensate for the tumor motion during the time delay in NIFT-TRT. I was doing, of course, a lot of literature search. And then in order to predict this non-linear tumor motion in 3D, neural networks seem to be the best way to go. So I used fully connected neural networks first. And this was, I think it's the era before the deep learning neural networks. It was like 10, 15 years ago already. And then these days I'm using recurrent neural networks. The aim here is to have less than 1 millimeter prediction error in 3D tumor motion over a possible time delay in NIFT-TRT, anywhere between 100 to 500 milliseconds range. I use recurrent neural network now because I really wanted to have an algorithm that can utilize the previous history or previous memory of tumor motion for future tumor position prediction. Because the main reason of tumor motion is breathing motion. And breathing motion, I mean, it's got some pattern in it, even though it changes all the time. During that a couple of minutes of beam on time, right? The radiotherapy, the actual beam on time is about 2-3 minutes, that's it. The breathing pattern should be staying more or less the same, and that's the assumption. Therefore, if you can use the previous memory, then it will be really beneficial for prediction. So I took the most famous RNN under the RNN family, LSTM, long short-term memory. And I was quite naive. I thought that if I build this big network structure, it may perform better in prediction, right? So I I constructed 2 layers of LSTM. Each layer has 256 units. And then fully connected layer at the end to output 3 coordinates for the tumor motion, X, Y, Z. Input in this case was previous tumor motions. This was quite complex, so it took about 3 hours to train per patient. But I didn't really care about training time at the time, because in radiotherapy, every patient has to go through something called the simulation session. So this happens about a couple of weeks before the actual treatment session. I have this 2 weeks of time to finish the training. But because now that I say because this was quite complex, I saw overfitting and the prediction outlier issues. You know, it predicts like my tumor is gonna be 20 centimeters away from my original position. That shouldn't happen in our body. So luckily I had a master's student at the time interested in this. So we were discussing again, how are we gonna make this thing better? And we were taking about the same approach. You know, maybe we don't need this big network structure. Maybe we can downsize, getting rid of all the overhead. So it's gonna make it faster. And then focus on to each patient's tumor motion, which is quite unique. So let's come up with the algorithm that we can optimize this structure for each patient, right? By the way, you may go through the same problem in your research project if you want to use in vivo data. It's really hard to get sufficient amount of data to train complicated neural networks. So I had to deal with this, work with whatever I had. What we found here was quite interesting and different from the previous example. So instead of using a single complex network structure, we were using very, very simple structure, just 1 layer. And then there's only 10 units in it compared to the 256 in the beginning, right? But what we did is we were training the same network structure, really simple one, but 50 copies of them. And the only difference was the random initial weight, right? So I think this is called ensemble network structure. And as an output, we were taking the consensus of those 50 networks. So we're taking the median value, right? Input is the same. Because this was a lot simpler and we were able to train everything in parallel, it's the same network structure. It only took about a couple of minutes to train per patient. So this opened up kind of new area of research for us, because before we always thought that we're gonna do the training before the actual treatment day. But now, because it's so fast, maybe we can train it right before we beam on, right? And the advantage there is we can use the fresh data, right? The most fresh data. So it was again ideal for NIFT-TRT real-time operation, and it showed less overfitting and prediction outlier issues. So these are a couple of examples. So 3D tumor motion, so left, right, end post, and supinf. The green curve is from predicted tumor motion, and the orange curve is from the true, like a known tumor position. So the more overlap they are, the better in this case. So this example is from pancreatic tumor, which shows some irregularities, as you see here and here. All of a sudden, it drops the one peak there. But the algorithm was dealing with it quite successfully, as you see. And then the error value was less than 1 millimeter, which is what we want in terms of root mean squared error. Another example here is lung tumor, right? It shows a lot more regular motion pattern. And this is pretty much what I expect in most cases during that few minutes. And error value was about the same, even though the motion range was larger than the pancreatic tumor case. So we applied this algorithm to more than 40 patients of data. The tumor types include lung, liver, and pancreas. Right around where 300 milliseconds time delay range, which is the most probable time delay in NIFT-RT, the error value was less than a millimeter. So we were quite happy with the performance. Okay, so far this is my experience and my mistakes on 2 examples. I have a couple more minutes. I'm gonna finish with one experiment that I did and then start taking questions. So I was talking about NIFT-RT for many years. I wasn't calling it NIFT-RT at that time, but at the end of my PhD, I have to show something, right? Physical demonstration, so people will believe me. So I had this experiment done. So I have a moving target in the linac-MR, as you see here in this animation. The target was simulating lung tumor motion. And then I was able to follow the target only with the radiation controlling the MLC. So I was doing imaging and irradiating at the same time using our prototype linac-MR system, as you see here, right? So here's my target. I have a gel that is MRI target, and then I inserted the film so I can measure the radiation exposure. And here's the result. This is a film result. Let's see, where's my cursor? Yeah, there. So this is the one from static target, non-moving. So this is the gold standard, okay? And this one here is the one from the moving target with NIFT-RT applied. So if you think about it, the radiation delivery to a moving or non-moving target should be identical if you can track it perfectly, right? So if I just compare these 2 cases, visually, there's very little difference. If I compare the radiation dose profile along this dashed line, and here's the result. And well, it matches well. That's what I'm trying to say. So it was less than 1% difference in terms of beam width. So that was good. And if you imagine there's no NIFT-RT, then you have to irradiate this much extra area, right, to deliver sufficient dose to the moving target or tumor in this case. So the whole point of my research is to try to avoid those unnecessary radiation. Okay. And I like to acknowledge, of course, my physicist colleagues. Special thanks to radiation oncologists who spend hours and hours manual contouring my images. And of course, my wonderful trainees. That's why they have all the pictures, and my funding sources. Thank you. Yeah. I'm sorry, whether, what was that? Ultrasound? Ultrasound, yeah. Right, so that's the exact reason why people tried it and then we're not really doing it. So people use ultrasound for different body parts, like prostate, I think they're using ultrasound. But I mean, there's a limitation in ultrasound in terms of depth and the resolution, image quality. So we thought, well, MRI is the best, obviously. So let's go with that. And it was considered not possible for many reasons, physics and engineering. But like I said, now we have it. So it's my director's baby, not my baby, but now we have it. So yeah. Okay, I guess I convinced everybody.